The title of the modulo, Integer Modulo n. In this module, we are going to see about integer modulo n. For learning about Zn, we should know some basic concepts like equivalence relation, equivalence class, etc. We will learn the concepts one by one. Let's start with the equivalence relation. Definition: a relation tilde is an equivalence relation on a set A if it satisfies the following properties. 1. Reflexive property: A tilde A for all A belonging to the set A. Symmetry: if A tilde B, then B tilde A for all A comma B belongs to A. Transitivity: A tilde B and B tilde C, then A tilde C for all A, B, C belonging to the set A. So, tilde represents equivalence. Let's see some examples. Number 1, equality is an equivalence relation. Number 2, let A be the set of all vectors in R squared. If A comma B belongs to A, define A tilde B to mean that A and B have the same length and tilde is an equivalence relation. Number 3, for x comma y belonging to R, define x tilde y to mean that x minus y belongs to the set Z. Reflexive property: let x belong to R, then x minus x is equal to 0 and 0 belongs to Z. Symmetric: let A comma B belong to the set of all real numbers. Suppose A tilde B, this implies that A minus B belongs to Z, the set of all integers. Then B minus A equals minus of A minus B, which belongs to Z, the set of integers, thus B tilde A. Transitive property: let A, B, C belongs to the set of all real numbers. Suppose that A tilde B and B tilde C, thus A minus B belongs to Z and B minus C belong to Z. Then A minus C can be written as A minus B plus B minus C. So, A minus C belongs to Z, the set of all integers. Therefore, A tilde C. It now follows from the definition that tilde is an equivalence relation on the set R, the set of all real numbers. Using the equivalence relation, we can easily partition the set A. The partite sets are named as equivalence class. The definition of equivalence class is: definition, if tilde is an equivalence relation defined on the set A and A is an element belonging to A, let equivalence class be defined as the set of all x belonging to A such that A tilde x. This is called the equivalence class corresponding to A. The examples of equivalence class are: number 1, if A is Z, the set of all integers, and tilde is congruent modulo 6, then the equivalence class 2 is equal to the set of all integers 2, 8 so on up to infinity and minus 4, minus 10 so on up to infinity. Integer modulo n is a one particular example of an equivalence class. Let's see it briefly. First, we start with a congruent modulo n and gradually we move on to integer modulo n. The definition of congruence modulo n: let n be a positive integer. For integers A and B, we say that A is congruent to B modulo n and we write A is congruent to B mod n, provided A minus B is divisible by n. The next theorem states that congruence modulo n is an equivalence relation. Let us see how it is. Theorem: congruence modulo n is an equivalence relation on Z. Proof: let n be a fixed integer. Define a relation on Z by A tilde B if and only if n divides B minus A. Clearly, A tilde A, since n divides 0, and A tilde B implies B tilde A for any integers A and B. So, this relation is trivially reflexive and symmetric. If A tilde B and B tilde C, then n divides A minus B and n divides B minus C. So, n also divides the sum of these two integers, that is a minus b plus b minus c equals a minus c. So, a tilde c, and hence the relation is transitive. So, the relation is an equivalence relation. From this theorem, we have proved that congruence modulo n is an equivalence relation. If we have an equivalence relation, then we can easily form an equivalence class. So, let us see the equivalence classes of congruence modulo n. The definition of congruence class of modulo n. Equivalence class n is equal to the set of all b belonging to Z such that b is congruent to A mod n, and that is equal to the set of all b belonging to Z such that n divides b minus A. That is equal to the set of all b belonging to Z such that b minus A is equal to Qn for some q belonging to Z. That is equal to the set of all b belonging to Z such that b is equal to A plus Qn for some q belonging to Z, which further can be written as the set of all A plus Qn such that q belongs to Z. These are different ways of writing congruent classes of modulo n. Now, we know that congruence modulo n, and we have congruent classes of modulo n, and from that we can easily form an integer modulo n, because integer modulo n is nothing but a collection of all congruent classes of modulo n. The definition is as follows. Integer modulo n. The integers modulo n is a set of all congruence classes modulo n. In symbols, it is represented by Zn is equal to the set of all congruent classes of An such that A belongs to Z, the set of all integers. That is equal to the set of all equivalence classes 0, 1, so on up to n minus 1. Let us see an example. Z3 is equal to the set of all equivalence classes 0, 1 and 2, and it has exactly 3 elements. On the other hand, every integer is in one of the 3 classes 0, 1 or 2, depending on its remainder upon divided by 3. So, equivalence class 0 is equal to the set of all integers 0, 3, 6 so on up to infinity, and similarly on the negative side minus 3, minus 6 and so on up to infinity. The equivalence class 1 is equal to the set of all integers 1, 4, 7 so on up to infinity, and on the negative side minus 2, minus 5 so on up to infinity. The equivalence class 2 is equal to the set of all integers 2, 5, 8 so on up to infinity, and on the negative side minus 1, minus 4 and so on up to infinity. The next one is the arithmetic operation on Zn. Arithmetic operation on Zn. A. Addition is defined as equivalence class A plus equivalence class B, which is equal to equivalence class A plus B. Multiplication is defined as equivalence class A times equivalence class B is equal to equivalence class AB. The next example will show you about the arithmetic operation on Z8. Example, let n is equal to 8. Consider the sum of equivalence class 10 over 8 plus equivalence class of minus 17 over 8. This is equal to equivalence class of 10 plus minus 17. Since 10 is equal to equivalence class 2 and equivalence class minus 17 is equal to equivalence class 7, then equivalence class 10 plus equivalence class minus 17 is equal to equivalence class 9 minus equivalence class 1, as well as equivalence class 10 plus equivalence class minus 17 is equal to equivalence class minus 7. This is equal to equivalence class 1 over 8. From this example, we can easily understand that there are so many different ways to write the same congruent class. Let us see if all congruent modulo n forms a group or not. Theorem: Zn is an abelian group under addition. Since we have to prove that it is an abelian group, we will have to prove 5 properties, namely closure, associativity, identity, inverse, and finally commutative property. Now first we shall prove the closure property. Let equivalence class A over n and equivalence class B over n belong to the set Zn. Then equivalence class A plus equivalence class B is equal to equivalence class A plus B, and clearly this belongs to Zn. That is, n divides A and n divides B implies that n divides the sum of A and B. Hence, Zn is closed under addition. Next we shall come to the associative property. Let equivalence class A, equivalence class B and equivalence class C belong to Zn. Then equivalence class A over n plus equivalence class of B plus C over n is equal to equivalence class A plus equivalence class of B plus C over n, which is equal to equivalence class of A plus B plus C n, which is equal to equivalence class of A plus B plus C over n, and that is the same as equivalence class of A plus B over n plus equivalence class of C over n, which is equal to equivalence class A over n plus equivalence class of B over n plus equivalence class of C over n. Hence, associativity also holds. Next we come to the identity property. Clearly, if there is an element equivalence class A belonging to Zn, then there exists a 0 element equivalence class 0 belonging to Zn such that equivalence class A plus equivalence class 0 is equal to equivalence class A over n. Hence, the equivalence class 0 is the identity for Zn. Similarly, the equivalence class A plus equivalence class of minus A is equal to equivalence class 0. This is for the inverse property. We need to find an element such that the addition of that particular element to our given element results in the identity element. So, clearly the equivalence class minus A exists, and therefore, the equivalence class minus A becomes the inverse element. So, inverse also exists. Finally, we come to the commutative property. Equivalence class A plus equivalence class B is equal to equivalence class A plus B over n, and this is the same as equivalence class B plus equivalence class A over n. Therefore, commutative property also holds for equivalence class A over n and B over n belonging to Zn. So, since we have satisfied all the 5 properties, Zn is an abelian group under addition. Now, we shall see some examples. Z4 addition modulo. This is the first example we are going to see. Now, the Cayley table has already been drawn, and you can see that 0 addition modulo 0 is 0, and so on. 0 addition modulo 1 is 1, 0 addition modulo 2 is 2, 0 addition modulo 3 is 3, and likewise for 1 equivalence class 1, 1 addition modulo 0 equivalence class 0 is 1, 1 it is 2, we are adding the 2, then 1 addition modulo 2 is 3, and then 1 addition modulo 3 is actually 4, but when you divide by 4 it becomes 0. Similarly, for 2 addition modulo 0 is 2, 2 addition modulo 1 is 3, then 2 addition modulo 2 is again 0 because it is 4, but when divided by 4 it becomes 0. Then 2 addition modulo 3 is 5, but when divided by 4 the remainder is 1, and likewise for 3 it is 3, 3 addition modulo 1 is 4, and therefore 4 divided by 4 is 0, 3 addition modulo 2 is 5, 5 when divided by 4 is 1, 3 addition modulo 3 is 6, but when divided by 4 it becomes 2. Now, when you look at the table on the whole, you can see that none of the elements are repeated row wise or column wise. So, you have 0, 1, 2, 3 here, 0, 1, 2, 3 here. You can see in every row and column that the elements might be in different positions, but they are not repeated. So, from the Cayley table, we can draw the conclusion that Z4 addition modulo is a group, because associative property will hold, closure property will hold, identity is there. Can you tell me what is the identity? The identity is 0. And similarly, when 2 addition modulo 2 is 0, which means that 2 itself is the inverse of 2. Similarly, for 3 addition modulo 1 is 0, and 0 being the identity element, so 1 becomes the inverse element of 3. So, inverse elements exist, and you can check even the abelian property here. 1 addition modulo 1 is 2, and similarly 1 addition modulo 2 is 3, and similarly 3 addition modulo 2 is also the same element, and therefore you can see that A addition modulo B is the same as B addition modulo A, and therefore commutative property also holds, and therefore we can draw the conclusion that Z4 addition modulo is an abelian group. Now let us consider the same group but under multiplication. Next we shall come to Z4 with respect to multiplication modulo. Again I have drawn the table for it. So you can see that the elements 0, 1, 2, 3 are placed on row wise as well as in the column wise, and now we shall do the operations. So 0 multiplication modulo 0 is 0 throughout for all the elements, because we know that 1 times 0 0, 2 times 0 0, and therefore this entire row is filled with 0. But when it comes to 1, 1 times 0 is 0, 1 times 1 is 1, 1 times 2 is 2, and so on. So again we have filled up the table here. But now when you look at the table itself, you can see that when 0 has got no other elements in the column, clearly it cannot be a group, but we will come to that later. 2, when you come to 2, 2 times 0 multiplication modulo 0 is 0, 2 multiplication modulo 1 is 2, 2 multiplication modulo 2 is 4, but when divided by 4 the remainder is 0, and therefore it is 0, and 2 multiplication modulo 3 is actually 6, but when divided by 4 it becomes 2, and here you can see that it is filled like this. And 3 again multiplication modulo 0 is 0, 3 multiplication modulo 1 is 3, 3 multiplication modulo 2 is 6, but when divided by 4 it becomes 2, 3 multiplication modulo 3 is 9, but when divided by 4 it is 8 plus 1, so the remainder is 1, and therefore we have filled up with 1. Again when you look at these two rows, you can see that this is filled with entirely 0 and this is filled with 0, 2, 0, 2, there is no 1 here. Clearly 1 is the identity element here, which is a multiplicative identity of this group. 2 does not have a multiplicative identity, and therefore Z4 multiplication modulo is not a group. You might suspect that by removing the 0 elements, the set Zn star, that is equal to the set of all equivalence classes 1, 2, so on up to equivalence class n minus 1 with multiplication modulo might be a group. Unfortunately, this is true for some values of n, but not for all n, as shown in the following two examples. Example 1, Z6 star, that is the set Z6 minus 0, is not a group with respect to multiplication modulo, since Z6 star is not closed under multiplication modulo. How is that? Because 2 multiplication modulo 3 is 0, which does not belong to Z6 star. The next example is, we comes to Z5 star multiplication modulo. Now Z5 star is a set consisting of the elements 1, equivalence class 1, 2, 3, 4, etc. But we do not have equivalence class 0 here. We are omitting 0, and that is why we are representing it by Z5 star. So I have represented it in the form of a Cayley table. You can see the elements 1, 2, 3, 4 here, 1, 2, 3, 4 here, and after doing the multiplication modulo, these are the elements we get. And we can see that none of the elements are repeated in each row and each column. You can see that the elements are not repeated and all the elements are also present, and therefore closure property holds. But we can see that equivalence class 1 happens to be the identity element of this group, because 1 multiplication modulo 1 is 1, 2, 3, 4, they are replicated here. Therefore 1 is the identity element here. And when it comes to 2, what is the inverse element of 2? So it is corresponding to that element which you get 1. Therefore this is the place where you get 1, and therefore this is 2 multiplication modulo 3 is 1. So we know that 2 multiplication modulo 3 is 6, but when divided by 5 the remainder is 1, and therefore for 2 the multiplication modulo 3 you get the identity element as 1 and 3 becomes the inverse element of 2. Similarly, for 3 it is corresponding to 1, corresponding to 2 you have 1, and therefore 3 multiplication modulo 2 is again 6, but when divided by 5 it is 1, and therefore 2 happens to be the inverse element of 3. Similarly, for 4 if you check, you get here 1 here, therefore 4 multiplication modulo 4 is equal to 8, but when divided by 5 it is equal to 1, and therefore you can say that 4 is a self inverse, because the inverse of 4 is 4 itself. Now, from this very table you can see that there is identity element, the closure property holds, there is inverse elements for all the elements, and therefore, and you can also check that even the commutative property holds, and therefore we can say that this particular group Z5 star comma multiplication modulo is actually a group. We will now characterize those elements in Zn star that have multiplicative inverses in Zn star and establish a condition on n for which Zn star is equal to the set of all equivalence classes 1, 2, so on up to n minus 1 is a group under operation multiplication modulo by the use of the next result. Let us see the result first. This is a well known result. If a and b are integers not both 0, then a comma b is equal to 1 if and only if ma plus nb is equal to 1 for some integers m and n. Next, we shall see a theorem in which we shall characterize which are the elements in a group that have multiplicative inverse. Earlier, in an example Z4 comma multiplication modulo, we saw that the element 2 did not have inverse, but the element 3 did. So, this theorem will tell us which are the elements that will have multiplicative inverse. So, the theorem, the equivalence class A belonging to Zn has multiplicative inverse if and only if A and n are relatively prime. Now, the proof, suppose that A has a multiplicative inverse B. In that case, A multiplication modulo B is equal to 1, equivalence class 1, which implies that AB is congruent to 1 mod n. This is from the definition, and therefore, this can be written as AB is equal to NQ plus 1. So, this part is a necessary part. We have assumed that this element has multiplicative inverse, and we are going to prove that they are relatively prime. So, AB is equal to NQ plus 1, AB minus NQ is equal to 1, and suppose that the A comma n, that is the GCD of A and n is equal to D, then D will divide AB, because D divides A and D divides n. Therefore, D will divide AB and D will divide n, therefore, D will divide NQ. So, obviously, D will divide AB minus NQ, but what is AB minus NQ? It is equal to 1. Therefore, D divides 1, but the only GCD or the greatest common divisor that will divide 1 is 1 itself. Therefore, D is equal to the A comma n, the GCD of A comma n, it is definitely going to be 1. The D cannot be any other element other than 1. Therefore, we have now proved one part of the theorem. Coming to the converse part, now we have to assume that A comma n is equal to 1 or that A and n are relatively prime. We need to prove that this element A belonging to Zn has a multiplicative inverse. Now, assume that A comma n is equal to 1. So, the GCD of A and n is 1 implies that Ma plus Qn is equal to 1. Bring this to the left hand side, Ma minus 1 is equal to minus Qn, or in other words, because minus Q times n means that Ma is congruent to 1 mod n. So, this implies that the equivalence class M times multiplication modulo equivalence class A is equal to equivalence class 1. In other words, the multiplicative inverse of A is M. Therefore, we have proved that this element A has a multiplicative inverse. So, we have created a condition for which elements the multiplicative inverse will exist. The next theorem follows from the previous theorem. Every non-zero element of Zn has a multiplicative inverse if and only if n is a prime number. Thus, Zn star multiplication modulo is a group if and only if n is prime. Let us see the proof. Suppose that the element A has a multiplicative inverse for all 1 less than or equal to A less than n. Then by the previous theorem, we know that A is relatively prime to n for 1 less than or equal to A less than n. This is true only if n is prime, because if A is relatively prime to every other element, then A is relatively prime to 1, 2, so on up to n minus 1. So this is possible only if n is prime, and therefore we can say that n is prime. Conversely, suppose that n is prime, then A is relatively prime to n for every 1 less than or equal to A less than n. By the previous theorem, we already know that the equivalence class A has a multiplicative inverse for all 1 less than or equal to A less than n. Hence, we have proved the theorem. We have seen in the previous results that Zn star under multiplication modulo is a group when n is prime. We will next consider subsets Un of Zn star such that Un is a group with respect to multiplication modulo for any positive integer n not necessarily prime. The next theorem, for each positive integer n, let Un be defined in this manner. It is the set of all equivalence classes such that 1 less than or equal to k less than n, and k and n are relatively prime. Then this particular set is an abelian group. Clearly this is a subset of Zn, and we are going to show that this subset becomes a subgroup. So we know that in order to prove that a subset is a subgroup, it is enough to show that the closure property and the inverse property are holding true. If we prove those two properties alone, it is enough. So we go by the first property, which is the closure property. Proof: let equivalence class A and equivalence class B be defined from Un, and we know that the GCD of A comma n is equal to 1 and the GCD of B comma n is equal to 1, because that is the condition that we have given for Un, and because of this condition we have these integers r, s, t and u such that ar plus su is equal to 1 and bt plus nu is equal to 1. This is from the GCD property, and we are doing a product of these two elements. Therefore, ar plus ns times bt plus nu. On the right hand side we have 1. So, the product of these two is again 1, and now we are going to group the elements in such a way that ab times rt plus n times these elements. So, because these are all multiples of n and this is equal to 1, we can say that A times A multiplication modulo B belongs to Un. So, we have proved the closure property for Un. The second property we must prove is inverse property. Now, let us take one element A belonging to Un, then by our condition GCD of A comma n is equal to 1. Again we use the same property, there exists integers r comma s such that ar plus ns is equal to 1. Bring 1 to the left hand side. So, ar minus 1 is equal to minus n into s. So, which means it is a multiple of n, and therefore, you can write this as ar is congruent to 1 mod n. So, we have now shown that A, the equivalence class A times equivalence class R is equal to 1, or in other words the equivalence class A has an inverse R which is inside this group, which is inside the set Un, and therefore, A is invertible. Now that we have proved closure property and inverse property, we can say that this particular Un, which is a subset of Zn, becomes a subgroup. In this module, we defined an equivalence relation, and from the equivalence relation we defined equivalence classes, and from the equivalence classes we defined a set called the integer modulo n, and from the integer modulo n we applied two different operations, namely addition modulo n and multiplication modulo n. We noticed that Zn under addition modulo becomes a group automatically, but Zn under multiplication modulo does not become a group, and it loses this advantage only because certain elements in Zn multiplication modulo do not have the inverse element, and therefore, we have to characterize which are the elements that will have inverse under Zn multiplication modulo. So, we come across this condition that Zn multiplication modulo, the element will have an inverse only if A and n are relatively prime. Using this condition, we discover that Zn star and the multiplication modulo becomes a group only when n is prime. I hope that this module on integer modulo n was useful to you. Thank you.